Welcome, everyone, to the Ontology Summit 2024 Fall Series. Today is the 25th of October, 2023. And today we have two speakers, and we're continuing the topic of ontologies and LLMs. So our host today is Andrea Westerinen. Andrea?
Hi, everybody. I would like to introduce our speakers. We've got hopefully a couple of great demos today about hybrid systems using LLMs with knowledge graphs and ontology engineering. And with that, I would like to introduce our first speaker, who's Evren Sirin. He's the co-founder and the CTO of Stardog. He has been working on knowledge graphs and ontologies and reasoning and all of those different aspects of AI since the early 2000s, is an expert on knowledge representation, graph databases, and semantic technologies. Evren got his PhD in computer science from the University of Maryland, College Park, and he was part of a group called MindSwap. It was a research group that was directed by Jim Hendler. He has authored many publications in computer science journals. He's been in bunches of conferences about knowledge graphs. He holds 3 patents in the area of knowledge graphs and is going to be talking, I think, primarily about Voicebox today, a new feature that Stardog has. Now, when we come to our second speaker, Yuan, he is a final year PhD candidate in computer science, supervised by lots of the big names of the professors and doctors at the University of Oxford. His research interests are in the area of neural symbolic AI, and he's especially interested in knowledge representation, natural language processing, those kinds of aspects of neural symbolic AI. His PhD is on adapting language models to a range of ontology engineering tasks that include ontology alignment, completion, embedding, and much more. He's interested in geometric embedding and the use of that in addressing the limitations of language models and representing logics. And those are our 2 speakers for today. And with that, I would love to turn it over to Evren.
Thanks a lot for the introduction, Andrea. Let me start sharing my screen and let's go. I hope you can see my screen.
I see it great. Perfect.
Okay, great. Yeah, today I'll be talking about Stardog Voicebox, LLM-powered question answering with knowledge graphs. Coming from industry, I'll be focusing more on the practical problems we have faced and how we solve them. I don't have too many slides, actually. I'd like to show a demo and a little bit of the inner workings of Voicebox and yeah, maybe answer any questions you might have. I'll start with introducing Stardog. Some of you might be familiar with it, but let me just give you a very quick introduction about the platform. It's a knowledge graph platform. We describe it as a flexible semantic data layer for answering complex queries or across data silos. Maybe one differentiating feature of Stardog you might not be familiar with, or maybe I'll start with, okay, knowledge graph term is a little bit overloaded these days. We are a knowledge graph platform based on RDF as the main underlying data model. RDF as an OWL for data modeling. We support reasoning and inferencing with OWL ontologies, as well as Swirl semantic web rule language. These are the kind of things we don't typically talk about, the technology and the standards, but since this crowd is mostly familiar with these, I like to mention them specifically. Yeah, one of the features that's might be a little bit different than what you would consider a triple store graph database is we also have a virtualization layer to access the external data sources in real time. The main query language we support is Sparkle, but when the user query asks Sparkle queries, we can translate them to SQL, execute them over the external data sources, and return the results as if everything is stored in an RDF model. This also brings some interesting possibilities as we start talking about the LLM integration. Okay, so LLMs have obviously created a big shift in all of the technology and maybe beyond IT with respect to how we are thinking about solving some of the problems we face, especially with respect to data management and knowledge management. And yeah, this is a general trend that we are seeing, though, is as much as LLMs and chatbots have gained attraction, lots of people are acknowledging the fact that LLMs by themselves are not do not provide the complete solution when we are thinking about a user trying to find answers to some questions. And coupling knowledge graphs with LLMs provide a much better experience for users to find their answers when they're dealing with this large enterprise data. So I didn't really talk much about the problems we or our customer face in general, but we are talking about large organizations, Fortune 500 companies that have thousands of databases spread across the organization with their own schemas, with own different teams managing those databases with different level of granularity with respect to how they represent information. And the way we see it, the knowledge graph, the ontologies provide us a way to connect those disconnected data sources in one unified graph view. And LLMs is the way for us to make these knowledge graphs easier to use for our end users. I mean, we've been working on in Stardog. The company was founded in 2016. We've been working on Stardog software even before the company was created. But one of the common challenges we see when we talk to end users is even the graph technology, basic RDF technology, even without coming to OWL or more complicated parts of the semantic technology stack, is not having familiarity with the technology. And LLMs provide us a way to basically provide a conversational interface to help people manage their knowledge graphs. So as I said, the platform has been around for a while. Voicebox is this new feature we've been working on since the last couple, 4 to 6 months, I should say. We are just launching our early access program this week, that's giving people access to use the very first version of Voicebox. That you can also go register and try yourself. I'll show a demo of what you would have access to in a minute. So Voicebox provides a couple different functionality. First is the creation of the ontologies, the knowledge graph to begin with, which is taking a user description of a model and then creating a very simple ontology to start with, or edit an existing ontology by new definitions as people want to extend their domain. I won't talk too much about this part. What I'll focus on today is the second task that we are focusing on, which is getting natural language questions from users, turning them into queries, and here Sparkle queries specifically. And based on the question, these Sparkle queries might have aggregations, comparisons, or all those kind of different expressivity that Sparkle has. And then executing those queries over the knowledge graph to return the results to the user. And reasoning and inferencing plays a role in this query answering part as well. Again, I'll show this in a little bit more detail in the demo. And the main point of, if you are familiar with the common ways LLMs currently are used today, we are doing something different with respect to how questions are answered. We are purposefully not trying to get the LLM to generate the answer. All the answers we are returning to the users are computed over the knowledge graph directly coming from the structured data. And that's a deliberate choice we have to prevent hallucinations as one of the main problems that we see with LLMs. I think everybody is probably familiar with the hallucination problem. LLMs, since they are trained to generate text, and as much as they seem to have a lot of common sense and understanding, their tendency to generate text makes them to generate inaccurate facts, things that are not rooted in actual facts very frequently, and that's even a problem that we are facing in Voicebox. Maybe I'll mention some of those. As I said, I don't want to talk too much about ontology creation. There's like a recorded demo here, but just to give you a flavor of what we are talking about, this is what you are seeing is Designer, our kind of simple ontology creation interface. So the idea is for you to go there and say, okay, I want to create an ontology about customer 360 use case, for example. And you would get some simple class definitions. LLM will not generate something very complicated out of just an initial one paragraph of description, but then you can go and make some changes manually and then accept those changes and then continue making changes to the model as you go along, maybe connected to some of those data sources. Here might be a little hard to see, but here the prompt is saying like, add a concept about rewards account. So there's a change to the existing model that we have created. So we kind of highlight what LLM is suggesting, and then the user has the option to accept or reject those changes. But okay, as I said, I'd like to talk mostly about the question answering part of the problem. And maybe I'll directly go into a demo to show you how this works in practice. So in Stardog, we have these things we call knowledge kits, which are basically sample ontologies and data sets to get people started with. And this is what we are giving users access in the early access program to try Voicebox. As you can see, these examples are from different domains. Maybe I'll start with something simple like this is a tutorial for some Stardog features, but it uses movie information. This is kind of how you can kind of browse through the graph and see its details in our Explorer tool, but I'll just directly go to this Voicebox panel where you'll actually see some sample questions we have put in here. So I'll just select one of these, and as you can see, so I just selected the question, find the directors who directed more than 25 movies. And then the response came back saying the following directors have directed more than 25: Woody Allen, Clint Eastwood, Alfred Hitchcock, Steven Spielberg. So what has happened behind the scenes is this user query that we have retrieved, we turned it into a query by looking at the ontology and what kind of terms are used. So here, for example, used in this very simple ontology. We have a concept about movie, organization, and person, some object properties, relationships between these concepts. So we align the user question with whatever terms are defined in the ontology, then use the LLM to create the query, execute that query, and then return the results back to the user as a text summary, again, leveraging LLMs in this case. Okay, so these are some examples here. Maybe I'll actually go for us. I'll go to this beer supply chain example and show some other things here. Let me try one of these examples. They take a while. LLMs are good at lots of things. Answering questions quickly is not one of their features. And also being consistent is not one of the things. As you can see here, I just selected one of these sample queries that typically works well, but basically the response we got back was the question we asked. So that's like one of the things we are working on to make the results more consistent. But very quickly, so this example, this is like a supply chain use case, specifically about beer as the product. So there are some raw materials, recipes involved, and equipments that generate the beer in different plants. Then they get shipped to customers, and then there might be some customer feedback about issues and things like that for you to kind of go back and find in your supply chain process. And here, for example, one of the queries I just now tried is list the names of suppliers and the number of customers they supply to. Okay, that's a very simple question. Now I'd like to go a little bit deeper into what's happening behind the scenes. And I'll switch to Stardog Studio. This is the environment where you can write Sparkle queries. So we have the Voicebox integrated here. And I'll try the same example. Okay, so once you come to this interface, you can actually see what query is being generated, and the results that are being returned as well. And you have the option to go back to the graph and to visualize these. But the point I'd like to make here is how we are making use of logical reasoning and rules in connection with the LLM. So this is a relatively simple query. As you can see, there's a concept about supplier, and we are asking for how the supplier is connected to the customers. And there's grouping and counting and those kind of things. But actually what's happening behind the scenes, and this is a little bit going into the weeds, but these plans show us how Stardog actually answered this question, and you'll actually see lots of other terms from the ontology being used while answering this question, because within our data, there isn't actually a direct relationship between suppliers and customers. If I can, okay, of course, Zoom is in the way. Let me do this. Right now, I'll switch back to Designer to show you that, okay, this is the ontology that we have for this beer supply chain example with those concepts about customers and all that there. But here we have also defined some inference rules. And this is the specific rule I'd like to focus on, which is telling us the rule for how a supplier is connected to a customer. So suppliers actually supply ingredients, they got used in recipes, which gets put into products, and those products are distributed through these things called skids, and eventually get to the customer. So there's all these additional relationships within the ontology before you can connect a supplier to customer. But with this rule, we have this direct relationship inferred. So when the LLM looks at the ontology, it sees this supplies term and uses it in the query. But when we execute the query, the reasoner within Stardog goes and looks at these definitions and answers the question based on these base facts. And this is also the other point of why we are doing Voicebox the way it is. You can have complete traceability for all the answers generated by Voicebox by looking at the query to see, okay, it's the supplies relationship. Then you can look at the ontology to see how the supplies relationship might be generated, and then go back to even these individual triples at the RDF level to see where they are coming from. But also it allows us to define rules to basically encode the business domain in a very specific and concrete way. For example, in the beer example, if there's a sensor in a truck that's carrying these beers and there's a temperature sensor where the temperature goes over 50 Fahrenheit, this is an anomaly. This might cause the beer to go bad, and that might be related to the customer feedback, for example. So we can have these kind of rules expressed as part of the ontology using the ontological terms, and the LLM can just use anomaly as a thing that it will query, but the actual answers are driven by whatever the business domain expert thinks an anomaly is, rather than what a user might, what an LLM might think. Okay, so I know we don't have too much time, so I'll just quickly go back to my slides to wrap up and answer questions. I think there are some questions in the chat. So this is a kind of a very quick overview of what I already described happening behind the scenes. So users ask the question. We have actually a vector database to kind of link those textual concepts with actual ontology terms. Then we do a little bit ontological reasoning to kind of expand those initial matches that the vector database returns. Then we send a prompt to the LLM to generate a Sparkle query along with these ontology terms and the user question that was asked. Execute the query, get the results back, and then use the LLM to summarize the results. Again, very quickly behind the scenes, we are using open source LLMs. We are not using OpenAI or ChatGPT. This is actually a very small LLM in the grand scheme of things, 30 billion parameter LLM compared to like trillion triples that OpenAI has. This foundational model was initially created by Mosaic ML, which has been now acquired by Databricks. It's an open source model. We basically took this model and fine-tune it with our Sparkle queries and ontologies that we created internally within Stardog, along with some of the benchmarks that has been used in academia. And then there's some vector embeddings and vector search, as I said, to align the textual concepts from the user prompt to those ontology terms. In summary, with Voicebox, we are, as you could have seen, it's a kind of very simple chat interface that you can put in front of end users to query a knowledge graph without knowing anything about graphs or Sparkle or any of those. All the answers are computed over the knowledge graph, which, as I mentioned, might be even virtualizing some SQL databases. This allows us to retrieve most recent proprietary data that these general purpose LLMs don't have access to. It provides complete traceability of answers back to the data sources. And we can also enforce access control rules when we are answering these queries. not every user might have access to the information about suppliers, for example. So when that query is executed over the knowledge graph, it would be executed with the access control rules, permissions that you have access to. So you might get different results based on your access level. And then, as I showcased, quickly logical reasoning is also leveraged. This allows us, even though LLMs can generate queries, as we have seen, they cannot generate too complicated questions, or they cannot make sense of very complicated ontologies. So these reasoning rules allows us to basically create simpler concepts, simpler relationships that LLM can understand and generate those questions. And here's the link. If you are interested in the early access program and would like to try this yourself, you can fill out this form. We are letting people in this week in batches, so you might not get access right away, but we'll be going through all the registrants and try to accommodate as much people as possible. Okay, I'll pause here. Maybe I see we have 2 minutes. There are
maybe maybe what we could do, Evren, is you could take a look. There's a lot of questions. And
yes, I was just
kind
trying.
of pick one. You can reply in the chat, and then people could also continue asking questions in there, and your replies. And we also ask questions on the our Ontology Summit channel, Google group, via email. And I just don't want to overrun Jan's time. So if that would be okay, maybe we can do that. And then if you have a chance to hang on, we can ask some more questions too at the end.
Yeah, I see. I'll try to I'm trying to quickly go over the questions. I'll see one question from Peter about the language used to express the rules. Yeah, Todd said it looks like swirl rules. Yes, it's swirl rules. We have a little bit extensions to swirl in Stardog, both syntactically and also a couple additional things, but we can express them in swirl as well. What open source LLMs did you find adequately trained? Maybe I'll mention this very quickly, and then I'll try to answer the rest of the questions in chat. I don't want to take time from our next presenter. With respect to open source LLMs, we've looked at, started with smaller models, with 7 billion parameter models that we have seen were not adequate in their first of all, without fine-tuning, none of these open source models are very good at generating Sparkle queries. If you go to OpenAI, it will do a decent job, even out of the box. But the open source models at 7 billion, they don't generate good results, but even fine-tuning or prompt engineering doesn't improve the results too much. MPT 30 billion was one of the models we have found good with respect to the trades-off for scale versus accuracy. With fine-tuning, we were able to get decent results with it. It's more amenable to prompt engineering if you are familiar with things like chain of thought or those kind of things, more things you can do in the prompts to guide the LLM to generate correct answers. With smaller models, that kind of prompt engineering doesn't work. You need to go to higher ones, but this is an ongoing process for us. We are continuously evaluating different models, their accuracy, the speed, and all those kind of things, because hardware constraints is also one thing you need to consider whenever you are working with LLMs, because even if you are willing to pay a lot of money to run these LLMs on these expensive GPUs, you cannot find them on Amazon or other providers. So yeah, there might be some other questions.
Everett, let's close this discussion now, and because it's 12:31, and go to Jan. And I want to thank you for that. And there is lots of interesting questions in there. So
yeah, I'll try to answer them as I listen to the next presentation.
Great. So if you can stop sharing, and Jan, you could start.
Yeah. Let me see. Desktop. Can you see the screen clearly?
Yes. Yes.
We can. Could you go to slide share, slide presentation? Yeah, presentation mode. Great. Perfect. Thank you.
Yeah, thanks for Evren for the excellent talk. So I will continue my presentation about a DeepOnto, a Python package for ontology engineering with deep learning and particularly language models. So as Andrea has already introduced me, I will skip the introduction of myself and but actually the original motivation for DeepOnto was founded on my PhD works relating to language models and ontology engineering. But later on, we found there are many basic features that can be encapsulated and be potentially used by the community. As all these kind of things scale up, we finally propose DeepOnto as a standing package. So I will first introduce the ontology, which I think most of the audiences in this summit are familiar with. So ontology is an explicit specification of a conceptualization, and here conceptualization means the model of domain-knowledge. The term sets are explicitly specified a set of entities, including concept properties, instances, and the relationships among them. A famous ontology language is OWL, which is a standard recommended by W3C, equipped with high expressiveness and reasoning capabilities. Ontology engineering concerns different stages of ontology development, such as design, construction, curation, and more. There are several challenges about ontology engineering. One is about scalability, because knowledge is ever expanding. And we need to assure the quality of the developed ontologies. And also sometimes we want to merge data from heterogeneous sources to achieve data integration. So all these challenges were previously heavily relying on manual labor. So now we want automation. So, so a solution for automation is to build an ontology engineering system with deep learning and a particular technology for that is language models. So, and to fit the need, we introduced the package on DeepOnto. So DeepOnto is a Python package, and here we will briefly cover the overall architecture, our dependency choice, the central processing API that can be, I think, the most useful for the community, and some of the tools and resources we have already developed based on our API, and also the long-term stability of the package, and finally some impact and use discussion. So I will first introduce the overview of the package. So as you can see from the figure here, the bottom side is a central ontology processing API, and with some low-level our dependencies supported, and there's a central, the base on ontology class is surrounded by various kind of ontology processing modules, and they collectively support the development of the tools and resources subject to different kind of ontology engineering tasks. And we also have deep learning and other dependency to support the development of the systems. And the tools and resources can actually incur backlit requirement to further enrich the ontology processing modules. So this is kind of a simple development cycle of DeepOnto. So our main dependencies are our API for basic ontology processing features, and PyTorch for deep learning framework, and Hugging Face transformers for language models. Yeah, these are the main dependencies. There are, of course, others, but we just list a few that are very important. And so why do we use Java here? That's because previously reliable and stable ontology APIs were mainly built with Java. such as our API, JCEL, and more. And we actually tried to build the package solely on Python, but we didn't succeed to do that because originally DeepOn2 was built on this API called R-Ready2, but it lacks several essential features. And if we build everything from scratch, requiring considerable low-level engineering efforts, and we don't want to give up existing efforts, so that's why we built, we utilize the our API as one of the low-level dependency. And why do we use Python? That's because mainstream open source deep learning frameworks such as PyTorch, TensorFlow, Keras, and so on and so forth, they are all Python based. And it's easy to use. For example, if I want to load a pre-trained distilled BERT, this is a kind of BERT model available in the Hugging Face. So we can just use 2 lines of code to load the pre-trained model. So to bridge the 2 programming language, we use JPipe. Now I'm going to introduce some of the features of our basic fundamental ontology processing API. The base class is ontology. So here, DeepOn2.on2 is a path for the submodule of DeepOn2 related to the central processing API. So the base class ontology encapsulates the base fundamental features from the our API. Such as accessing, manipulating entities and axioms, querying for annotations, parents, children. A reason for that's why we need to encapsulate this feature is that in Java often we need a few lines of codes even for simple functions like that. So basically we want to promote a convenience of use. And then we have reasoning. So ontology reasoner here, which is to conduct reasoning ontologies, such as verifying entailment consistencies, and some more complex reasoning subject to particular tasks. And we currently support 3 types of reasoners: Hermit, which is sound complete on OWL, and ELK, which is tailored to the OWL profile, and a simple structural reasoner. We also have ontology verbalization. This is to process a complex concept into natural language text, particularly useful for models that take textual inputs, such as language model-based ones. So on the right-hand side, this figure shows an example that our recursive algorithms performs on a complex concept, food product, and exists derived from invertebrate animal or vertebrate animal. So this complex concept is passed into a sub-formula tree and then recursively merge into a final natural language sentence: food product that derives from invertebrate animal or vertebrate animal. Yeah. So yeah, this is to this module actually facilitates the text processing part. And then we have pruning. So sometimes we want to extract some sub-ontologies for a scalable experiment. So in DeepOn2, we implement an algorithm that tries to reconstruct the subsumption axioms for a class that will be removed. So as can be seen from the figure here, if the blue node it represents a class that will be removed, then we reconstruct subsumption axioms between its parents and children to preserve the hierarchy. Notice that the nodes can represent complex classes as well. Yeah, and a potential future work for this line is also to trying to preserve logical modules of the pruned ontologies. We also have a ontology to graph features. 2 of them are implemented here. So this is often required in graph-based deep learning applications. An example here is that we have translational embedding like trans-E and ontology embedding like auto vector star. And we have ontology projector, which essentially is to project an ontology into triples. and also an ontology taxonomy, which is can be seen as a special case of projection, where we extract sub-subject hierarchy from an ontology. But although this is a special case, but the functionalities and are different, so we separate them into different modules. They are all for supporting graph-based applications. And then we have more processing modules as well, such as normalizer, which is to normalize axioms into basic forms to support logical embedding. And a future work called ontology modularizer, where we want to extract logical modules for a given set of axioms. So all these processing modules aimed at transforming ontology into various kind of data formats to support downstream deep learning-based ontology engineering solutions. So they are the building blocks for the tools and resources. And DeepOnto currently also incorporates some developed tools and resources for ontology alignment and completion. So here, ontology alignment in our context is a task of identifying the set of mappings which indicates semantic relationship between entities from different ontologies. And ontology completion is the task of identifying a missing semantic relationship between entities within the same ontology. This task is sometimes similar to the link prediction task in logic graph, but of course, ontology supports more complex logical structures. So for ontology alignment, we have the first system called BERT-map for concept equivalence ontology alignment. The architecture of BERT-map was shown here. It takes two ontologies as an input, and additionally, no mappings or even complementary sources like some relevant auxiliary ontologies. They are optional. And then turning ontologies into a text coupler used for fine-tuning downstream BERT model for classification. And because the naive traversal of ontology alignment requires quadratic complexity, often ontology alignment system will be equipped with a candidate selection process for simply to select some low candidates before performing predictions. So we also have a subword inverted indices for this process. And we also have a string match module to filter some easy matching, because as in equivalence matching, there are some concepts that have exactly the same names. So after the prediction feeds, we have a set of scored mappings. They are further refined through an iterative mapping extension algorithm, and then finally a logical repair algorithm. And for ontology alignment, we also have a resource for both equivalence and subsumption matching. This is used in the OAEI ontology alignment evaluation initiative since 2022. So now we have two versions, and this year's results is about to be finished. If you are interested in that, you can check our report, which will be available in International Semantic Web Conference this year. And for ontology completion, we have a first system called BERT subsumptions for predicting missing subsumption relationship between ontology concepts. It's actually a sibling system of BERT-map, but the difference here is it utilizes templates, different kinds of templates to embed the subsumption sequences. And it also construct corpus from ontologies, and it supports both intra-ontologic subsumption prediction, also closed ontology subsumption prediction. So this is another setting for ontology alignment as well. We also have a Ontolama, which is originally a work for language model probing, to probe if a language model encode any kind of conceptual knowledge that are available in structural knowledge bases such as ontologies. However, the probing methods based on the prompt learning can be adapted to ontology completion as well. And surprisingly, actually, in this work, we found that language model can perform quite well on subsumption prediction just with few short learning. And actually, prompt learning is now actively used in large language models as well. So there are more tools and resources to be expected, and ontology engineering itself actually has a diverse range of tasks, not only alignment and completion. Even settings within alignment and completion vary, but we just hope that our basic ontology processing API can be serve as a foundation for all kinds of applications. And in the meantime, we will also build some of the tools and resources on our own. And DeepOnto will continue to incorporate more tools and resources, including some of our ongoing work for ontology embedding, concept ingestion, and more. So for the long-term stability of this package, we consider the following factors. First, we actually pre-process our API into JAR files, and then they will be shipped upon package installation. So those files will not be changed when we update the version of DeepOnto, because our API is fairly comprehensive for low-level ontology processing as already. So because of that, our ontology processing features should be quite stable. And for deep learning frameworks, although they are rapidly developing, but you know, as we all know, a lot of investment were put into deep learning framework development. So they are actually actively maintained for backward compatibility. So and we also provide some documentation about a system requirement and known to work commands for the users to successfully use our package. In terms of impact and use, as far as we know, it has been adopted by Samsung Research UK for developing digital health coaching, and another one is Madrid Digital, whose main goal is to bring new technology to the Spanish capital's administrative system. And for research side, we have it has contributed to the BioML check of the OAEI. And we also, beyond that, we actually have received a lot of help requests for research internship, microservices, and all kinds of requirements. And because DeepOnto is still a young package and getting attention from the community, so we think all those ongoing works could probably turn into some real work in the future. So all kinds of feedback and help feature requests are extremely welcome here. So this summarizes my talk today, and for more details, you can visit our website for the package. And I'm not sure if we have time. What's the time now?
You definitely have at least 5 more minutes, sir. Okay.
So yeah, do you have some questions, or should I present the website for like a demo?
I would love to see a little demo. That sounds amazing.
Okay, sure. Okay, so so this is a website of the DeepOnto package. So where we have like a lot of support about how to install the package and the main features, and the tutorials about some systems and tools, and the package reference where you can see very detailed parameter attribute and the explanation of them. And hopefully all this can be very convenient to use and clear. Yeah. As for the code demo, I think we don't really have time for that now. So yeah, if you have some question, you can try it on. It's just a Python package, so easy to install. Yeah.
Well, that sounds great. So maybe if there are questions, in the chat, and I know people are trying to answer them. So, but maybe if somebody really wants to talk, like Ravi raised his hand, maybe we'll just go raise your hand if you want to ask a question or put it in chat. Let's do it that way.
Okay.
My quick question is a very interesting way you approach ontology alignment. In the past, we've been talking of integration. You take it to a different and deeper level of matching the semantics of the underlying concepts and underlying semantic meanings. How much have you succeeded in aligning using this?
Okay, so in our tool, in our current implementation, so one of the reasons that we integrate the language model into the process is that it was famous for contextual embeddings. So we can actually embed context into text, and also, for example, the rule-based systems, they don't really know the linguistic variation, such as synonyms and paraphrases and so on. So yeah, so with the help of the language models, our systems can actually predict some of the alignment that cannot be predicted by previous rule-based systems. And as for the effects and the performance, I think you can maybe check on the BioML check. There are various systems available on the website, and probably you can see their results on many kinds of ontologies. Yeah.
Thank you. Thank you. Tell us a little bit about OAEI, if you can.
So yeah, OAEI is a ontology alignment evaluation initiative. So yeah, I think it was launched back to 2011, if I remember it correctly. So it's co-located at the International Semantic Web Conference, and it now has, I think, more than around 10 different tracks for ontology alignment and knowledge graph alignment. Yeah, so I think if you just type OAEI ontology alignment evaluation initiative, I think you can already see the website. Yeah.
Thank you.
Do we have anybody else who wants to ask some questions? We have some time of either speaker.
I will stop sharing maybe.
Thank you for that talk, by the way.
Thank you.
I know there are lots of questions and people have been doing a great job of answering them just as they go along in the chat. Bart, you wanted to say something. Please go.
Sure. This is a question about traceability, and I'm just going to pick up on John Soa's question. Whenever you type anything in English, the system should produce an echo in English to show exactly how your input was interpreted. So I think it's a great question, but I'd like to expand on it a bit and just ask, is there an explainable component to your model? We all know that LLMs are not explainable, so I'm wondering if there's some insights into how the reasoning actually goes on in your model. Thank you.
Yeah, we don't have an explainability for the LLM part. So how the LLM generates a query from the user question, we can't explain that part. But what we are relying on here is the query itself can be inspected and analyzed and used for traceability itself. So that's the part when we say we can trace the answers we produce to the actual data points, because it's a structured query. We have all the details we need to explain that part. But yeah, we are not at this point looking at the problem of like, how can we explain why the LLM came up with those ontological terms based on the user question. So, and traceability in that sense right now requires more technical knowledge about what RDF and Sparkle is. So it's not at the level of like a regular end user can get that kind of explainability at this stage, but that's something we are exploring, how to make that information a little bit more accessible.
And Juan, can I maybe pass the question to you as well? How explainability works in your model? Thank you.
Oh, you mean, okay. It's me, right? Okay. Yeah, explainability. So we actually have, like, for example, in our BERT model, we have so actually it means that language models are not good at explaining its results. So that's why we need some additional tools that utilize existing semantics from knowledge bases to help with that. And for example, in our BERT model, we have a logical repair as the final step. This is to somehow reduce the impact of the maybe hallucinated results from language models. So yeah, that's one approach, but there are so many approaches to be explored. Yeah.
Thank you.
Mike, thanks. Mike Bennett, you had a kind of interesting question about ontology alignment and top-level ontologies. Did you?
Yeah, if I missed it, I had to drop off for a bit. But looking at Yuan's slides, and you have this alignment and adding or removing subsumptions and things and squaring it all up. And I just wondered, does any of that sort of based on having a particular top-level ontology, like you have relative things or quiet entities or occurrence or 4D or anything, or conversely, if not, can you kind of build it around starting from a specific top-level ontology, like a realist one like BFO or like a Dolce or like a 4D one? Is those techniques applicable in those different kinds of ontology styles, or does it come with all its own style and its own set of top-level partitions?
Okay. If I understand the question correctly, you basically asking about like different style of ontologies, if they are all supported by our package or something.
Right.
Yeah, I think so actually, because we use our API is the low level dependency, and our API is fairly like compatible with all kinds of ontology syntaxes, as can be seen from Protege. And so we adopt our API for that. So I think most of the ontology formats can be processed with our package. And our algorithms are not based on a particular flavor of ontologies. Some of them, yes. For example, the normalization algorithm is for the EL profile, but most of them are quite compatible with all kinds of formats. Yeah.
Fantastic. Thank you.
So maybe at this point, I'll leave the meeting in the chat open, but I want to thank both of our speakers. We're up at the top of the hour. This was really, really interesting. If people have specific questions, you can send them to me and I'll forward them on to our speakers. I don't want to force our speakers to join our mail list. But otherwise, we are going to have a summary discussion. I should probably turn on my video again since I'm talking. We are going to have a summary discussion on November 15th, and we have 2 more very interesting sessions coming up. Another one about demos and these hybrid systems, similar to what we've been talking about today, but different, similar but different. And then some more broader thoughts discussion on November 8th, and then try to do a synthesis discussion, pull things together on November 15th. So if anybody wants to send key thoughts, things to talk about for the 15th too, please just send them to me. Send them on the Ontology Summit mail list. And with that, I will turn it back to you, Ken, to close it out.
Thank you, Andrea.
If Ken is.
And thanks to the speakers and all of the participants. We have had quite an impressive discussion in the chat. I will be posting the recording for those who couldn't make it to this meeting, and then Andrea is going to be posting the chat. All of this will be on the session page. And now I would encourage everyone to come next week. And I believe, Andrea, you're going to be speaking. Is that right?
I am, as well as the CTO from Lead Semantics. And so we're both pretty much, I already put up our abstracts and our titles. And we're basically talking about using LLMs to populate an ontology to get knowledge, to populate a knowledge graph. So
Sounds
hopefully
great.
that should be interesting for people. And yeah, as part of mine, I'm going to talk about all of the ways that I failed just using Spacey and NLP alone.
Well, that's going to be interesting. Lessons learned is always useful.
Yes.
Yeah, it's basically lessons learned, but also a demo of what are the prompts and, you know, what I'm trying to get at. So.
Oh yeah, no, I'm just saying we need more of that. Anyway, and so with that, we'll adjourn and hope to see all of you next week, November 1st, and a little, I believe, be careful about daylight savings time. It has ended in Europe. Next week it will have ended in Europe, but not here in the United States. So be careful about the time for this session so you don't end up missing it because of that. So thanks, everyone.
And to be clear, the time will be as advertised in North America rather than the European equivalent, just so you know which of the two to align with.
Yeah, so I'll be careful about that. And if you go to the session page, there is a world clock where you could find out what time the session will be in your time zone. So bye now.